There we go. People are walking in. Wow, the room fills up fast. All right, oh, we got a waiting room. Let's see, how do I do this? Benjamin, what'd you do? You came in as a guest. All right. All right, how's everybody doing today? Get the chat bar up. Okay, so I did not put a new homework assignment up because the last one is the one that you should be working on. I moved the due date from yesterday to next week. So that means you still have problems to be working on, right? Does anybody want to ask me any questions about the homework set that's out there right now? No? Everybody's good? All right, then what I'd like to do today is to show you, we did an example last time. I think we went through kind of fast on one that had polar coordinates. My job for you, with you guys today, is to introduce you to how we're going to handle general coordinate systems. And it's going to require a little bit of a step back from doing integration. So we may not actually do very much with integrals today. So I'm going to take the example that the kind of example that we had last time in polar coordinates, and I'll use that as my stepping stone to get you guys started so that you understand what this is all about. And by the way, the key word in here is transformations, which you saw in the homework set. But I don't know that I don't think we ever made it clear exactly what that means. So let me write down an integral for you that's going to be done in polar coordinates, and then we talk about what exactly we're going to do with those polar coordinates. Swing this thing around. Getting good at this part now. Now you remember, your job is to tell me when I need to scoot the paper over. All right, let's make this a little bigger for myself. I can't make it work. Hang on. There, okay. All right, so how do polar coordinates arise when we're trying to do integration problems? Sometimes I give you an example like this, where I ask you to integrate some function over some set S, and it's, let's do an area integral. This is a two-dimensional integral, so S is the subset of the plane. We've already talked about how you can use Fubini's theorem to write this as a double integral, and you have to you scan your whole region looking for the least and the greatest values of, let's say, the y coordinate, and then holding the y fixed, you look for the x coordinate. And the thinking there is that this is how you measure a little bit of area if you split your set S up into little pieces that have their boundaries lined up with the lines where this variable or that variable are staying constant. So that, in the Cartesian setting, that gives you a bunch of boxes. And the way that you get the area of the box is measuring how wide it is in the x direction and how tall it is in the y direction.
Professor, can I ask a question?
Yes, please.
Well, it's not about the math. I'm just saying, do you have any settings on your camera? Could you maybe change the focus or increase the contrast or something?
I don't know.
I don't know.
The short answer is no, because I mean, there's no like buttons on it or anything. Okay. I take it it's too faint. Is that the problem?
Yeah, it's a little faint and blurry, especially on the right with your double integral. At least for me, maybe someone
No,
else is
no,
different.
that's quite plausible. Let
Someone
me,
else say if they're having the same problem or not.
to be honest, I sort of see it in my own display. Of course, I know what I'm writing, so that helps. Let me switch to, get some markers out here. That might help. If they're not dead. No, that's dead. So, no, that's no better, is it? It's funny, it looks nice and dark when I start writing, and then when I move my hand away, it gets faint, and I don't know what.
It's a little better than your previous pen, but
is it?
It's not quite.
I remember the green markers you used. Those were really good.
The green marker? That's the reason that I wasn't reaching for that is that it's kind of fat, but maybe
Oh,
fat is
yeah,
better.
that's good.
That's
Though.
better?
Yeah.
All right, let's go with that.
If it's fatter, it's a lot more visible.
Okay. All right, then we'll do it. Thank you for telling me. All right, so let me get back to my display here. All right. So we followed the idea of Fubini to break the set S up into little boxes lined up with the coordinate axes. And then last time we said, yeah, but what if your set S is something like this? I think we had an example where we used a quarter disk. Because trying to split this thing up into little squares, it seems kind of not appropriate for the purpose at hand, because you're always going to have a bunch of squares off on the edge that are not complete. That feels irritating. And it shows up when you try to write the limits of integration, because if I wrote things this way, I would have y going from 0 up to whatever the radius is. And then the x coordinates would also start at 0, but you'd be stuck with some messy kind of formula like this for your upper limit of integration. So when you see a set like this for your domain S, it's very tempting to want to switch everything into polar coordinates. And you certainly can, but the big caveat that we had last time was that when you want to measure the area of a region that's found by splitting things up along the lines of constant polar coordinates, then it's not just a dr d theta. So the picture that would apply in that case is, I'll just write the whole thing again. When you want to compute the integral over, let's have it be a quarter of the unit disk, and then you've got some function of two variables in here. To compute this integral, you go through most of the same steps that we used for Fubini's theorem in Cartesian coordinates. Of course, if you're not going to use Cartesian coordinates, you have to get rid of them in the description of the function itself. You replace every x with an r cosine of theta, and you replace every y by an r sine of theta. And then you go back to, like I said, you do exactly the same steps that we had in Cartesian coordinates. You can decide which order you want to put your variables in. And if theta is on the outside, then over here you put the least and the greatest values of the theta coordinate anywhere in your set. So let me draw the set a little more carefully, a little bigger for you. We look at the lines, the sets of points that have a fixed theta coordinate, and we know that the theta increases when you move that way. So, right, theta is increasing as you move that way. So the smallest theta coordinate is the clockwise most point, which would be any of these, and they have a theta of 0. The largest theta coordinate is the counterclockwise most points. That's any of those. And you know they have a theta coordinate of pi over 2. Then we need to fix a theta coordinate. So you'll hold theta fixed at a constant value. And just within this line segment, you look at the possible values of the r coordinate. Now the r's, the sets of points where r is constant are these. And making r increase forces you to go outwards away from the origin. So the minimal r coordinate occurs right here at the origin. The maximum occurs right here at the outside of the circle, and that would be, if this was the unit disk, that would be an r equal to 1. So setting up the limits of integration worked very much like it did for Cartesian coordinates, except I need to remember that instead of saying westmost, eastmost, northmost, and southmost, I need to say words like clockwise most, counterclockwise most, inward most, and outward most. And along the way, I've drawn the lines where r stays constant, and I've drawn the lines where theta stays constant. Excuse me, I should say curves, where those two things stay constant. All of that feels very much like Cartesian coordinates, but then at the very end I said, oh, and there's an extra factor of an r. So my job today is to explain why that r is there and what you're going to do instead of an r if you have some other coordinate system. So the answer that I gave you last time was that, oh, well, you see, in order to get the little bit of area of one of these pieces, you need to know how to calculate the area of a sector, a portion of a sector of the circle. So each one of these sectors looks like the pie piece from Trivial Pursuit, but we've only got a portion of that pie piece split along a couple of concentric circles. And the way to get the area of such a little piece is to multiply the length along this edge, how much the r coordinate has changed. But then you also need to multiply by the length along this edge, and that's not just a question of how many degrees or radians you've increased as you move from left to right. But you need to take that change in the radians and multiply it by a factor of r, because you obviously have more area enclosed when you're further away from the origin in the first place, even if the dr is the same, and even if the d thetas are the same. This one's obviously got more area than that. Sorry, my phone has got some spam, I guess. Yeah. Okay, now I'm going to set the integral aside and just focus on what I did here with these coordinates. So you probably feel happier doing these things in polar coordinates because you realize that your limits of integration on both the r and the theta are now constants. In principle, these two expressions could have been functions of theta when I try to use the process of setting up the limits of integration a la Fubini's theorem. But they are in fact constants, which means if you only look at the combinations of r's and thetas, I'll put, I guess I don't care, I'll put r's on this axis and thetas on that axis. All of the combinations of r's and thetas that you see in this picture come from a rectangle in r theta space. These limits of integration say that the thetas should range from 0 to pi over 2. Here's where theta is equal to 0, and here's where theta is equal to pi over 2. And independently of which theta you choose, between those two numbers, you're going to have r coordinates that vary from 0 up to 1. And that's, as I say, that's true for every intermediate value of theta between theta equals 0 and theta equals pi over 2. All the thetas give you the same range of r's. So all of the combinations of r's and thetas that you get in, well, I can think of that pair of numbers as giving you a point in what I will call r theta space. All of these combinations come from this rectangle. It's not a square, despite my picture. It's actually taller than it is wide. But this is a rectangle that somehow corresponds to this quarter of a disk that I had in the first place. Now, there is a pretty natural kind of a correspondence. I mean, you have the formula that tells you how to get a point in the x and y plane from the r and theta coordinates. I've already used it up here. This is the formula that tells you how to get the x coordinate and the y coordinate in terms of the r and the theta coordinates. You need to stop thinking about just the formulas, though, and think geometrically. That pair of formulas is actually giving you a function, a transformation, that's going from this two-dimensional plane, this is R2 here, and it's carrying you over to a different two-dimensional plane, the one in which I'm using x and y coordinates to determine my location. So we have a function that goes from R2 into R2, and we even have explicit formulas for it. Let me call it capital T. Let T be the name of this function. So capital T is a function from R2 to R2, 2 inputs and 2 outputs. And exactly the formula for it is that T takes 2 inputs, which I can call R and theta, and it creates 2 outputs, which I could call X and Y. But this is the formula that says how we calculate the inputs from the outputs. So you have always just been thinking about changing the coordinates. You're just looking at this little picture that looks round. And yet, now I'm asking you to think about 2 separate copies of the plane, one of which has that same round figure in it, but the other has this rectangle in it. Now, let me show you. Actually, I wonder if I can move this camera around. Let me show you something here in my office. Oops. It doesn't have as many degrees of freedom as I'd like. Can you guys see? Look, there, perfect. Right here. You see this? This is a portion of the XY plane with the lines of constant theta going that way. And when I squeeze this, it turns into the picture in the other copy of R2 that has the radial lines. Did you catch that? In other words, if I take, this is the picture of my window shade. Oop, now I gotta turn it down towards again. So my window shade has those horizontal folds that go this way. And what the little clip does is it grabs all of the points along this left-hand edge and it squeezes them essentially to a single point. And when you do that, these horizontal lines kind of fan out and they give you these lines that are all coming apart. They come away from the little clip that glues them together. The reason that that matches this formula is it explains exactly in pictures what this formula is doing. All of these points along the left-hand edge are points that have an R coordinate of 0. When you stick in an R equals 0, it kind of doesn't matter what the theta is anymore. You're just going to get an X coordinate of 0 and a Y coordinate also of 0. So all of the points over here get sent to just that one point. In mathematicians' language, we would say that the transformation T is definitely not a one-to-one function. It has multiple inputs that give you a single output. But apart from that issue on the left-hand edge, what's happening is all of the other folds on the blind in my office, those are parts of these lines where theta is being held constant. So when you apply this transformation to all these points in a single line segment, you're applying this transformation to all the points that have a fixed value of theta, then you'll get a particular number here and a particular number there. But as you let R vary between 0 and 1, then you're just going to be multiplying both that cosine number and that sine number by the same factor. As R increases from 0 to 1, you start off at the origin and you gradually move outwards towards the end of the unit circle, the edge of the unit circle. Okay, so in this picture, I've shown explicitly that these are the points that have a fixed value of theta. Theta equals a constant. But you already know that from the way you draw, the way you use polar coordinates in the plane. These are precisely the sets of points that have a fixed value of theta. They don't have a fixed value of x, because that would be a vertical line, nor a fixed value of y, that would be a horizontal line. But they have a fixed value of that other function, theta. So, and by the way, you can do the same thing by looking at the sets of points that have a fixed r coordinate. I mean, what happens to this straight line, all the points that have r equal to a half? Well, when you put in r equals a half in this formula, but for different values of theta between theta equals 0 and theta equals pi over 2, you get all of the points in the plane whose polar coordinates have an r equal to a half, but the thetas vary from theta equals 0 to theta equals pi over 2. So this, like I said, these horizontal lines turned into straight lines in this picture. They're not horizontal anymore, but at least they're straight. On the other hand, the vertical lines in this picture, those are the sets of points that have a fixed R coordinate. They got turned into a curve. They're the set of points that wrap around the circle at a fixed radius. I'm sorry, they wrap around the origin at a fixed radius. So I get it that you're used to just using at the XY plane. You look at a point and you ask it about its R and theta coordinates instead of its X and Y coordinates, and you're comfortable with that. But you do need to remember that as soon as you've written down the R and the theta coordinates, why, that's just a pair of numbers, and therefore you can think of that pair of numbers as representing a point somewhere in an R theta space. And all the combinations of R's and thetas that you need started off in this rectangle. So this is the way we're going to be using this in these integration problems. Effectively, what you are doing when you say you're going to change coordinates is that you are introducing a new transformation that redescribes the region that you're integrating over in terms of a region in a different copy of the plane. And by the way, when we have a three-dimensional integral, we'll have the Cartesian coordinates shown in one picture. You'll have some other version of R3, and then a transformation that goes from R3 to R3 to squish around a new region and turn it into the region that was given. You'll see, we'll do the three-dimensional pictures anyway, coming later. Now, one of the things that you notice about this, this pairing of these two different pictures, is that the funny shaped regions that I used when I set up this integral, these little portions of the pie piece, those are exactly what comes out of this transformation when I start off with exact rectangles in this picture. So I've got so many cross marks, I want to draw it again here. We're starting off with this rectangle in R theta space. The R is going from 0 to 1. The theta is going from 0 to pi over 2, by the way, is a little more than 1.5. That's why I'm drawing this thing taller than wide. One way, oh, sorry, and then as I said, the transformation changes that into this quarter of a disk, the quarter of the unit disk. Now, we know that when we're doing an integration problem, we have to split up our region of integration into smaller pieces so that we can play the whole game of what an integral is about. And when polar coordinates are floating around, it feels natural to create little regions by drawing those little pieces of the sectors that I had earlier. They have their edges being a pair of, well, they're actually rays where theta stays constant, and then a pair of circular arcs on which R stays constant. Such a little region is exactly the image under this transformation T. It's the outputs under this transformation T of a rectangle in this space. You see, when I said I wanted to stay between those two circular arcs, that means I wanted the R coordinates to vary from some small number to some other number that's just a little bit larger. And likewise, if I wanted to stay in this wedge where the theta coordinates vary from something to something, well, that means that the theta coordinates in this picture have to vary from some number to another number that's just a little bit larger. So, although I've chosen to split my set S into funny shaped regions when viewed in the XY plane, in the R theta plane, those regions are not so funny looking. They're just little rectangles. Moreover, I had some difficulty in deciding on what the area of this one was, but in this picture, the area is now very easy to figure out. The area of this little rectangle it's the same kind of thing that we said when we were discussing Cartesian coordinates before. You look at how wide it is, and you look at how tall it is. Those are the lengths of these two line segments. And when you multiply those two things together, you get the area of this piece. Unfortunately, you know that this transformation T is not preserving area. When you have a little section of this picture and then apply the transformation to all the points within it, you're going to get another piece over here that does not have the same area. And area is a crucial thing to keep track of exactly when we're doing these integral calculations. We're supposed to be evaluating a function at different points and then multiplying by the area of the little pieces. So it's but the definition of the integral asks me to do is to multiply by the area of this piece. And this piece is created from this piece in a very natural way, but they don't have the same area. So here's the thing you need to ask yourself. How much does area change when you apply a transformation T? If you have a transformation T that moves points in R2 and gives you other points in R2, then it will do things like move little rectangles and squish them so that they turn into other little patches of the plane that are not even rectangles anymore. Although they're not rectangles, they still have an area, and you'd like to ask, how do I calculate the area of that little piece from the area of this little piece? This is the one that's the area that's easy to compute, but this is the area that we need for our integration problems. Well, I have an answer for you. And the answer is that if you're in the vicinity of a particular point, let's just call it P here. So here's the theorem. At any point P in R theta space, areas are going to get stretched when you apply this transformation T. Areas are stretched, well, stretched or shrunk, by a certain factor. In other words, whatever the area is of the little region that you've got around the point P, then approximately speaking, and you get equality in the limit, approximately speaking, the area of this little patch will be stretched or shrunk by just multiplying that area by a factor, and that will give you the area of its image under the transformation T. And I know exactly how to compute that factor. To get that factor, what you do is compute the derivative of the function T. Let me just pause for a second here. We've talked about differentiating functions that go from Rn into Rk, and you may recall that that derivative is a k by n matrix. In particular, when you go from Rn to Rn, your derivative at each point will be an n by n matrix. So I take my derivative calculation, I evaluate it at my point P, that'll be a square matrix, and then take the determinant of that square matrix. And because I know that areas always should be positive, I'll throw in an absolute value sign. So that is the theorem that I'm going to try to work with you guys on for, it'll take me all of today to make you feel kind of comfortable with it. The application for us is going to be that in our integration problems, when you take your set, like this quarter disk, and decide to chop it up into little pieces in this fashion, and you ask yourself, how am I going to compute the area of a little piece that's like this? Well, you recognize that this piece comes from, this piece here is the image under this function T of a little rectangle in this space, and the area of a rectangle was easy to compute. That was the dr d theta. So then I just need to stretch that area by this fudge factor. I need to put this in as the absolute value of the determinant of the derivative at P of the transformation function. So when you switch from using Cartesian coordinates, I should have labeled my axes with Cartesian coordinates. When you rewrite the problem in Cartesian coordinates as a problem in polar coordinates, you need to replace the little area element, not by dr d theta, but by a dr times d theta times this fudge factor. I told you last time you needed to replace it by just r dr d theta, and now I'm telling you something that looks a little different, but that it only looks different because I tried to put it into a more general context. If you retreat to the very particular context of using polar coordinates, then I have an explicit formula for capital T, and that will allow me to calculate what this fudge factor should be. So let's write out the function capital T. T at any point r theta is calculated as r times the cosine of theta, comma, r times the sine of theta. And now I can compute the derivative of T. So remember, when you have a function that spits out more than one possible output, you compute the derivative of that function by taking the gradients of those different outputs one at a time to be the different rows of your matrix. And the gradient just means it's the row consisting of all the possible partial derivatives of that function. So I need to differentiate this function with respect to both r and theta. Here's the derivative with respect to r. Here's the derivative with respect to theta. And that's my top row. That's the derivative of this function of two variables. In the bottom row, I'll have the derivative of this function of two variables, and by derivative, I mean the gradient, so the collection of all the partial derivatives. You have to differentiate in the same order as before, r and then theta. So the derivative with respect to r is the sine of theta, and the derivative with respect to theta will be r times the cosine of theta. So it's these derivative calculations that we were doing earlier in the semester that now are going to have to show up. I need to emphasize that this is not the derivative of the function that I was trying to integrate in the first place. I never told you what function I was going to integrate. It didn't matter. This is the derivative of the transformation function, the function that rewrites Cartesian coordinates in terms of polar coordinates. Now, you guys do have to remember how to compute the determinant of a 2x2 matrix. For a 2x2 matrix, you know that that's the product of the things on the main diagonal minus the product of the things off the main diagonal. So what I will get will be cosine of theta times r cosine of theta minus sine of theta times negative r sine of theta. And I think you can see what's happening here. The first term is r times cosine squared of theta. The second is going to be plus r times sine squared of theta. But cosine squared of theta plus sine squared of theta is equal to r. And in our case, all of the r coordinates are positive. They're between 0 and 1. So I don't need the absolute value signs. And that means that the area element will in fact be r. That's the absolute value of r times dr d theta. Okay, and that's the formula that I discussed with you last time. Last time, my focus was on trying to help you see how we would compute the area of a little region like this, and there was a certain amount of hand waving where I said, yeah, it's almost the same as a region like that had parallel sides and so on. But now I've found the answer in a different way by using this theorem about how much areas are stretched or shrunk in a transformation. This is the new theorem here that shows the role of the derivative and the role of the determinant in calculating the changes of area. I'm going to pause here for a second to let you guys kind of catch up on that. In fact, without writing anything, I'll just kind of talk you through this to give you a little more intuition if this makes any sense. So how that theorem comes to be is that you got to remember that what the derivative, how the derivative was really defined earlier in the semester was that the derivative was the linear function that best approximates the original function. So we're taking not the original transformation t, but at each point in the r theta space, we were coming up with a linear function that approximates capital T. And then you have to turn to somebody who's taking a linear algebra course and say, hey, if I have a linear function, how does the linear function change areas? And in a linear algebra course, you learn that that's the role of the determinant. The determinant is measuring how much a linear function can change areas. So let me now take another example, and I'll start it as an integration problem, but it's not really the integrating that is going to concern us too much. I want you to see the changes of transformations, and that will, I think, try to drive home a little bit what that theorem says. Oh, wait, before I do my other example, I did want to say one more thing. You'll notice that this claim here about how much areas are being stretched or shrunk, in the polar coordinates case, notice that the calculation that we've just given says that the fudge factor that says how much areas are changing turns out to be just R. What that should mean is that when you take portions of this picture, portions of this big rectangle, they don't even have to be squares or rectangles. Take a round portion of this rectangle. Follow through what happens to it when you apply this transformation T. According to this theorem, you should get something that's got its area stretched or shrunk by a factor of approximately what your R coordinates are. That means for a region that like the one that I've drawn over here, that's close to this vertical axis, if it's close to the theta axis, that means that your R coordinates are small. According to this theorem, that should mean that when I follow through what happens to this disk, I should get something in this picture that has a much smaller area. The area of this thing will be multiplied by R, but the R coordinates here are much closer to 0 than they are to 1. And sure enough, if you do what I did with the blinds and you just squeeze all of this, or trace through using the R cosine of theta, R sine of theta formula, you'll see that this circle gets changed into some sort of a squished circle. It's not quite an ellipse, but it'll be very close to the origin in this picture. It'll still stretch kind of far outwards because my R coordinates stretch from almost 0 to, well, something that's small but not tiny. Those R coordinates in this picture range from almost 0, so I'm almost at the origin, to something that's small but not really tiny. On the other hand, the theta coordinates are, a small distance apart over here, but when you do the squishing on the left side of the picture, then you don't get much room for variation in the theta sense. You don't change the angles too much. So it's a very squished little picture here. And sure enough, the area of this figure is going to be a lot less than the area of that figure. If, on the other hand, I had applied this transformation to a circle that was over here, well, again, I've got a certain amount of range on the R coordinate. So I'll get, my figure will stretch from just a little bit past this outer circle to, a little bit past. The R coordinates are going to vary a little bit in this picture. On the other hand, that small change in the theta coordinate that I see from the bottom of the circle to the top of the circle, once you're on the outside of the unit circle, a small change in the theta coordinate is going to give you a pretty big shape. I mean, these two circles might have just as much variation in the theta coordinates, but in this picture, you can see that giving them the same variation in the theta coordinates is giving you a squished circle on this side and a stretched circle on that side. So in this case, the area seems to have gotten bigger. And that matches with what we've just computed. If the fudge factor, the stretch factor on areas turns out in our example to be just R, well then, if you're in this region, your R coordinate is more than 1, which means that the areas are being stretched by a factor that's larger than 1. So this little disk shape is going to have a larger area than that one. Okay, so that's just another illustration just within polar coordinates of how areas are stretched or shrunk by a factor that, in our case, just turns out to be R. All right, you guys are really quiet. Does anybody have any questions you want to ask on this example before I give you a different example?
Yes, could you go back to the slide that you had up just after this? It was
This one?
prime equals the gradient. Yes, that one right there. Okay.
Okay.
So yeah, so just T prime equals just the gradient of both. Okay, that was just all the information that.
Right. In general, for a multi-valued function, for a function that goes from Rn into Rk, I would write down k different gradients. I just differentiate each of the k different component functions. So here's the derivative of the first, here's the derivative of the second, and if when we get to three-dimensional coordinate systems, you'll have the gradient of the third function will show up in the third row. Yep.
Thank you very much. And then, of course, you just took the determinant of that, and that's how you calculated
Yep.
that with R.
Yep. Yep. Everybody just seems to remember for polar coordinates that it's r d theta. But this is where that r comes from. It's actually taking the determinant of this particular matrix.
Great. Thank you very much.
All right, let me show you another example, guys. So here's my next one. Let me suppose that I ask you to calculate some integral of some function of two variables over the following region in the plane. I'll call it D because it's a diamond. So here's the set D. I want you to look at the set of all points that's bounded by these four line segments that are supposed to be parallel. So here I've got x plus y equal 1 is a line. Over here, x plus y equals -1 is a line that's parallel to that one. Here you've got the line where y is 1 less than x, and here's where y is 1 more than x. So those two lines are also parallel. Two lines with a slope of 1, two lines with a slope of -1. Now, if I asked you to compute such an integral, you guys, I hope, would realize that you could do this by means of Fubini's theorem. All right, let's actually do it. Let's get the limits of integration. I don't want to actually compute the integral, so I won't bother writing down what my function f will be, but I'll just write it as some function which you integrate with respect to x and y. And for some reason, I've chosen to put x on the inside and y on the outside, but you know you could go either way. I'll take the suggestion from you guys. What's my minimum y coordinate anywhere in this figure?
-1.
Yeah. So you should be looking for the southmost point, and I see it right here. What makes that point be what it is? Well, it's the intersection of these two lines. So from those two lines, I get two equations. And then from those two equations and two unknowns, I can solve for x and y, and I discover that y is equal to -1 and x is equal to 0. All right, so the same general procedure I've used before. And in the same way, my largest y coordinate is the y coordinate of the northernmost point. That's right up here. It's the intersection of those two lines. From those two lines, I get two equations. From those two equations, I get the y coordinate. Then, somebody want to tell me my least and greatest value of the x coordinate? What are you going to get as your least x coordinate? What should my lower limit of integration be?
Would your lower x component just be -1?
Well,
If you go all the way east.
how about if, no, all the way west is what you mean. For
Yeah.
lowest x coordinate. Yeah, does somebody want to respond to that?
I don't think you can do that. You'd actually have to probably split it into two integrals.
Why?
Well, because the farthest west you can go on the top is y -1, but on the bottom it's -y -1.
Okay,
Right?
so good. So you've actually objected in two ways to the prior answer. Yes, it's true. The minimal x coordinate that you see anywhere in this picture would be the x coordinate of the westmost point anywhere in the picture, which would be this point right here. And yes, its x coordinate is -1. But when you're getting your inner limits of integration, don't forget that by the time you pass inside these square brackets, you're supposed to be holding y fixed. And so you're supposed to fix your value of y to a constant and only look at the points within the domain D, within the diamond D, that happen to have this fixed y coordinate. And now you should be talking about your westmost point and your eastmost point and asking for what their x coordinates are. And again, I describe this point by saying two things about it. It's first of all on this line where y is constant, and secondly, it's on this diagonal line where y is equal to x plus 1. And so from those two equations, I could determine the x coordinate, which would be, well, x is y minus 1. And so that's what I would like to write down here. And I would like to write x is equal to, 1 minus y for the largest x coordinate. But as you said a second ago, that's actually inaccurate thinking. Everything that I just said is fine as long as I'm drawing this line of points that have a fixed y coordinate, as long as I'm drawing it in the top half of the picture. If you decide to hold that y coordinate fixed to some negative value between -1 and +1, in other words, if you draw that horizontal line, well then now your y coordinates are, your x coordinates will range from -1 minus y to y plus 1. So I can't even do this. In Cartesian coordinates, this has turned into kind of a mess. You would have to write this as a double integral over the, well, I'll write it this way. It's a double integral over the top half of the diamond plus a double integral over the bottom half of the diamond. And then on each one of those two separately, you can play exactly this game. One of them would have y going just from 0 to 1. And then if you know y is between 0 and 1, then you can write out the limits of integration like I had them. But in the second integral, you let y go from -1 to 0, and then your x coordinates would be something different. Okay, try it. I'll let you actually work out the limits of integration. Make sure that you understand why I had to split it up and how I would get those limits of integration. But the point that I'm trying to get at today is that maybe that's not the best way to do this. Maybe this particular problem could be better done with a change of coordinates. And here's how I want to do that. I noticed that in my diamond, there are two different quantities that are staying constant on the two pairs of edges. If I already wrote these two in the form of x plus y is a constant and x plus y is a different constant. I could do the same thing over here on these edges. This is where y minus x is equal to -1, and this is where y minus x is equal to +1. So here's my thinking. I'm going to have two new coordinates called u and v, and they're going to be exactly equal to these two quantities. So over here on the side, I'm going to say let u be shorthand for x plus 1, and let v be shorthand for y minus x. I'm sorry, I didn't say what I wrote. U is x plus y, and v is y minus x. Then I can use u and v as two new coordinates in this set. What are coordinates anyway? They're numbers of measurements that
Could you
you
move the
take.
paper, Dr.
Oh, yeah,
Zink?
sorry. Coordinates are measurements that you take that help you find your way in this space. If I tell you that I wanted to have u equals 1/2 and v equals 1/3, well, you could find what point that would be. If you want u to be 1/2, you have to be on the line where x plus y is 1/2. If you also want v to be 1/3, then you need to have y minus x be equal to 1/3. And so you've just told me that you want to be on both of those lines at once, and there's just one point over there. So you see, u and v are a pair of new coordinates that I'm using in this set. And that means that I've got a picture kind of like I had in the previous one. I've got a u coordinate and a v coordinate that I could measure, and each one of those pairs of measurements specifies a unique point in this diamond. Exactly the little formulas that I've written out for the edges of my square tell me that that diamond is the image of the set of points that have u coordinates go between u equals -1 and u equals +1, and the v coordinates range from v equals -1 to v equals +1. This is going to be a better coordinate system to use because in this coordinate system, my region of integration is just a rectangle, and that's where Fubini's theorem is really easy. So I'm going to try to do for this coordinate system what I did in polar coordinates before. Instead of trying to take my integral over the diamond and doing it in rectangular coordinates, I'm going to do it in my u and v coordinates. I'll have to replace all the x's and y's by some functions of u and v. I'll show you those in a second. But my region of integration is now this square. And that means that I'll write this as a limit. My limits of integration will go from u equals -1 to +1. V will go from -1 to +1. Look how easy those limits of integration are. Two things you're going to have to do, though, as a penalty. Life will still be difficult in some way. Number one.
Dr. Rusin, can you slide up the paper, please?
Yep, thanks.
Thank you.
The number one thing that you're going to have to do is to figure out how to describe this transformation, because I didn't actually do it for you. What those formulas are doing is they're actually telling you the reverse transformation goes this way. But it's easy enough to take these two formulas and solve. If you add these two equations, they would simply say that 2y's is what you get with u plus v, so y is equal to u plus v over 2. And if you take these two equations and subtract the top one minus the bottom one, then all that will be left on the right-hand side will be a 2x. And if I divide by 2, that will give me my x coordinate. So this is the formula that you need for the transformation capital T. This is the recipe that tells you how to get the x and y coordinates of a point, knowing the u and the v coordinates. This tells you where to put a point that you get, where do you put a point that started over here in this picture. That's the one penalty, the bigger penalty that you have to pay in order to make this transformation. That'll tell you what formulas to put into these two spots. The other penalty that you have to pay is that it's not just going to be du dv at the end. You have to put in that determinant thing that goes into this spot. So I will need the determinant of the derivative of the function t that I just computed. Fortunately, that's not too hard. I can calculate the derivative of this function by first differentiating the top output and then differentiating the bottom output. And when I say differentiating, I'm computing the gradient. I'm taking the partials with respect to u and v. So there's my 2 by 2 matrix, the determinant of which is 1/4 plus 1/4. And therefore, my conclusion is that the original integral of the original function of x and y integrated over the original diamond has now been written as an integral over the square, where u goes from -1 to +1 and v goes from -1 to +1. I take my function and I replace every x by that u minus v over 2, comma, replace every y with a u plus v over 2. And then I have to put in this determinant factor times the du dv. Okay, that's a lot. I know you're probably a little shell-shocked at this moment. But why don't I stop here and we'll pick up with this thing again next time. What I've just given you here, this is the change of variable theorem for multivariable integrals. We're changing the domain of integration, we're changing the variables that we're using, and we're even changing the little measurement of area calculations. That's the fudge factor that came in the previous theorem. So there's a lot of details in here, but trust me, this will be an easier way to compute this kind of an integral in general. It depends on what the function f is. This one is easier than that one, and so that's why we want to use these. Okay, is that too much for a day? Why don't you ask me a last minute question and then we'll go. Nobody?
So for these problems, you kind of sort of have to solve for x and y in terms of like your new created variables, right?
That's correct. I had to kind of poke around and figure out what my new coordinates would be, and then I had to do some algebra to figure out how to express the x and y coordinates in terms of them. So that little bit of algebra, you didn't have to do that for polar coordinates because you're used to expressing polar coordinates with the r cosine theta, r sine theta formula. That was already kind of given to you in polar coordinates. In this example, I had to invent those formulas. I deduced them algebraically after deciding what my new coordinates would measure. My new coordinates u and v measure the things that are calculated as x plus y and y minus x.
since the transformation, like, since your transformation, you have it like in terms of like U and V, right? And that's
Yes.
like, so like if you were to have like the opposite transformation, would it scale like the opposite transformation that's in terms of X and Y, right?
Yep, that's this
Would
pair
that
right
be
here.
like, right. Would that be like the inverse of the original scaling factor?
It exactly would
like
be.
2?
Yes,
Okay.
I invite you to calculate the derivative of this function. This is also a function that goes from this copy of R2 down to this copy of R2. If you calculate the determinant of this one, you'll find that that is exactly going to be a 2. You learned that in a linear algebra class, by the way, that the determinant of an inverse matrix is the inverse of the determinant of the original matrix. But you can also see it in this geometric sense. If this transformation is cutting areas in half, well, then the opposite one must be doubling areas. And by the way, this, you should calculate the area of this diamond. You'll see that it's exactly an area of 2, whereas this one has an area of 4. So yeah, this transformation is cutting areas in half, and this one is doubling them. Good questions. Okay, but they're good questions, and they took us way over, so I'm going to cut it here. But ask me these questions again on Friday, okay? Or ask the TA. Go. You guys should be using Piazza more. Go to Piazza and ask each other these questions and kind of talk it over, and the TA can help you. In fact, I can chime in if I have a minute. I'll go onto Piazza as well. Agreed? All right, guys. Tune in again on Friday, and we'll do more examples of this. I know this is hard, but it's really fun and useful.
Thank you.
All righty. Bye-bye.